For another talk. He's on a tear. Yeah, going to be talking about mechanical keyboards, so that'll be a fun one. Come out and geek out on some mechanical keyboards. Yes, Anna? You got an announcement? Come on up and give the announcement.
Hi, I'm Anna Sherman. I run CodexX. I also am an organizer for CHADEV. Next Wednesday at Hack Night, which happens on this floor at 6, we're going to be doing our second session for the new CodexX website. This helps you learn some process of how to get an app up and running. Last week we did an experience mapping with Allie, and this week we're going to do some wireframing with Jathan, our designer. So if you're interested in those things, you do not have to be a woman to come and participate. It's just a place that's safe and empowering for women to come and learn. So that's 6 o'clock on this floor, usually over that. Actually, no, sorry, I lied. This week it is going to be up on the 9th floor in the Carbon 5's office. So, yeah, also Hack Night will be in Carbon 5's office this week, not on this floor. So, just up a few floors on the 9th floor.
All right, so without further ado, we've got Colin all the way from San Francisco to give us a talk today. He's from Neeve Research, and he's our head of engineering. So you guys give a warm round of applause to Colin.
So thanks everyone for coming. So yeah, my name's Colin MacNaughton. I head up engineering at Neeve Research. Neeve Research are the founders of the X platform. Neeve was founded in 2008 on the realization that we were really at an inflection point in the marketplace where, due to the ubiquity of 64-bit computing and dropping costs of RAM, it really was starting to become possible to develop applications in which, as opposed to keeping memory on disk or in a database, we can keep our application state fully in memory. So becoming very easy to hold all of the working state that we need to write our applications right there next to the business logic that we're writing, right? So we're made up of a team that's really passionate about delivering architectures that are mechanically sympathetic with hardware. So if you're familiar with the term mechanical sympathy, it's really about developing applications in a fashion that is most compatible with the underlying hardware. And our sort of goal is to provide application architectures on which you can use hardware to its most efficient extent, right? So if we can use hardware really well, we can scale wider with less hardware. So we want sort of cost-effective architectures using as little hardware as possible. I need to speak louder? Okay. Can you hear me in back? Right, good. So the X platform's a sort of horizontal computing platform that allows you to write distributed applications by declaring event handlers that, based on message type, route events to your application and to allow you to write business logic in a really simple fashion, right, while leveraging state in memory. So it lends itself really well to streaming applications. We're in production on Wall Street, doing high-frequency trading, so running flows that are end-to-end in tens to hundreds of microseconds, ranging up to hospitality use cases, e-commerce, where it's a much sort of wider spread of applications, bigger distributed platforms with higher throughput constraints. So today I want to talk a bit about streaming and why in recent years streaming is really coming to the fore. What are the drivers behind that? And what are some of the challenges that we as application developers have to deal with when writing streaming-based applications? And how do we evaluate technologies and solutions to write these streaming applications? So I hope that you come out of this with a better understanding of what it takes to scale up these types of applications and some of the gotchas to watch out for when looking at the different technologies and infrastructure pieces you're going to use to build applications like this. And I'll introduce you a little bit to the X platform and how we tackle streaming as sort of an illustrative case on how you can do streaming very efficiently. And we've got a short time window today, but hopefully we can get into a little bit of a use case. So, you know, what recently has led to the rise of streaming? I think a lot of it has to do with technological drivers. more organizations are using memory-oriented technologies, which is allowing them to push and process data faster. Newer data stores like hybrid transaction analytical processing databases allow us to Hello. All right. Can you guys hear me better? Great. So anyways, new data technologies allow us to process data in real time and apply those outputs from large analytical loads in near real time. So we as businesses, we want to be able to take advantage of that like new stream of intelligence and work it into our applications. So the more quickly that I can respond to real-time data, the better I can capitalize on sort of business moments and make my applications better, you know, leveraging sort of opportunities that would be too transient to manage in sort of a batch type of system. So finally, I think the cloud's a bit of a driver too. It's, we're seeing organizations really begin to become more comfortable with cloud architectures. And as organizations are breaking down their more monolithic application approaches into multi-agent architectures that are service-based and launching them into the cloud, possibly on a hybrid of an on-premise or a cloud solution, now you've got these different applications that are not operating in the same process. And if we want to be able to scale, perform with a multi-agent distributed architecture, we need to be able to talk between these applications really fast and at low latency. So without further ado, you know, what does a streaming application look like? Kind of like any other sort of computing architecture, right? We're going to take some inputs. We're going to work on that input data against some sort of application state and arrive at a result which we're going to share with the rest of the world. So a streaming app is really no different than that, except that you've got sort of a fire hose of inbound events you want to process, and you need to be able to absorb all the changes you make from that processing very quickly, pushing it into whatever sort of data storage technology you're using. And finally, you need to be able to push the results of that huge stream of events you're processing out to other interested parties in the form of new streams. So what do you need to worry about? What are sort of the non-functional concerns that you have as an application developer when trying to assemble a solution that does streaming? Of course, because it's streaming, I think the first thing we think about is we want it to be fast. So for really sort of high performance data streams, we'd ideally like to be able to process, you know, tens to hundreds of thousands of transactions per second. So fast is sort of something that's sort of one of the first things we think about with streaming. It also has to be reliable. So as I'm processing streams of events and I'm saving state, like let's say I'm receiving an order from a customer, I need to get that customer order saved into some sort of database, some sort of data store so that I don't forget about it before I respond to that customer. So ideally as an application developer, I don't want to have to worry about what happens if my process crashes. Am I going to re-process that order and end up sending, you know, the customer two products? Finally, our applications need to be available, right? So in the event of software, hardware, or data center failure, we want to be sure that we can fail over and continue processing a stream of data without interruption. And streaming by nature, we don't always have control over what sort of data streams we're processing. So we want to be able to scale up elastically and handle spikes in the load. Plus, we'd also like to be able to, as businesses, be able to grow our applications such that they can you know, grow as we add new functionality into our applications. So those are sort of the non-functional tenets of writing a streaming application. And ideally, we want this to be easy from a development point of view. So I want to be able to write just plain business logic without thinking about these non-functional concerns. So I want to take a look at a couple different architectures to give you guys a sense of some of the bottlenecks associated with trying to do streaming at extreme volumes. One rule of thumb I keep in mind when thinking about streaming and infrastructure pieces is that when we think about streaming, we tend to think about how how fast is my system in terms of transactions per second? How many events can I process per second? And we don't really think about what the processing costs us, right? So there's an inverse relationship between the throughput and the processing latency when we're writing these transaction processing systems. So if it takes me a millisecond to process that order event, that's going to cap me at 1,000 messages per second because there's only 1,000 milliseconds in a second, right? And if I need to process these streams in order, that kind of gates the amount of throughput that I can sustain when doing streaming. Of course, I can scale wider and increase my sort of capacity as long as I don't have ordering requirements. So when we're looking at building these systems, we need to think about anything we might do in our logic that would block processing and can get us over that sort of 1 millisecond mark. And as a little spoiler, to really achieve tens or hundreds of thousands of transactions per second, you're probably going to be using an in-memory computing technology. So just looking back at our picture of what a streaming app looks like, when we're thinking about those microsecond hiccups that we need to worry about as application developers, this diagram kind of points out the types of things that you need to worry about. The most common one we kind of think of is that's going to slow down our transaction processing is the database transaction. We're going to do some processing, we're going to update some state, and if I'm talking to a relational database that has a transaction, I'm going to be making a call out to that database, which is going to slow down my ability to process that stream of events. Perhaps a little bit more subtle is if I want to make sure I'm not losing messages. Messaging is also an acknowledged protocol. So I've also got callouts for every sort of outbound event that I stream to downstream participants. If that call is synchronous, like say JMS persistent, that's also going to impede my ability to process events. So while we walk through some of the sort of different architectures we could consider, I just want to kind of keep those points in mind. So this diagram kind of gives you a sense of the sort of canonical transaction processing architecture. This would be like a J2EE, where I would launch several instances of my application into an application server and achieve a degree of scalability by launching several instances I can scale out wider to some degree. And then any of our applications can process a particular request, and I don't have to worry about ordering, providing I'm using transactions to the database, right? So if I've got an add customer request followed by an update customer request, and the add's processed here, and the update is processed there, then I'm fine as long as I'm using a database transaction to keep the state consistent. The problem with an approach like this is that it won't really scale horizontally after a certain point, right? If I've got to keep the state consistent amongst all of these instances, at some point the database becomes the real choke point for scaling out. So as we have more instances of our application trying to scale wider, the transaction consistency or concurrency issues at the database really starts to slow down our overall processing speed. So you're going to end up in a position where you're looking at like a couple hundreds of transactions per second, maybe up to 1,000 transactions per second, but nowhere near sort of the ability to scale. There are also some complexities for you as an application developer to think about when thinking about the communication layer with incoming requests. Because if I don't want to process duplicates, I need to then coordinate my add customer request, for example, with the update to the database. So if I want true exactly once processing, when I add the customer to the database, I want to ensure that I'm not processing that addition more than once. So that leaves you in a position where you're sort of managing transactions using something like distributed transaction coordinator, XA sessions, something like that. So that sort of transaction management tends to be persistent too, which also kind of violates my 1 millisecond rule. But in this architecture, the real is the single point database where we've got transactions and a lot of contention that prevents us from scaling. So that's where the sort of in-memory technologies start becoming relevant to reducing those choke points. So we first started seeing people introduce caches, so distributed caches, to start bringing the state a little bit closer to the application. And at least for read type loads, now I don't have to go and pull out from the database the data I'm looking at. And then data grids came along, and now when I'm doing a stream of updates, I can push into an in-memory data grid a lot faster because I don't have to synchronize to disk back in the data tier. So that takes you to a certain degree higher performance, right? But it doesn't really solve the underlying scalability problem. We still have the problem of, as we scale wider, the transaction and contention issues of managing state consistently between each of our application instances becomes a choke point. So in-memory technologies, in-memory caching, data grids, it does help you to a certain degree, but you're still looking at a single database choke point. So what are modern architectures doing to address this? If you're familiar with the microservices paradigm, microservices espouses a model where you start making state private to any sort of application, right? So I can decompose my application down into smaller pieces with their own private state, and then use more intelligent routing between these applications at the messaging layer to route the right requests to the right application. So if I can partition my application state by some sort of business reasonable metric, let's say I'm writing an application that's managing customer data, I can now stripe that state out between multiple instances. I can, let's just say on last name. And by doing that, that means I can get true parallelism because I am no longer now between my instances that I'm using to scale the application. I no longer have contention between them. And that's really key to being able to scale much wider in an elastic fashion. So if we want linear scale, you're definitely going to be looking at how do you break down your application and partition on state via a reasonable business metric to you. What that implies at the messaging layer is that you need to have a bit smarter routing, right? Because someone's got to route the right request to the right place. So you'll be using some combination of content-based routing or a richer topic space to make sure that the clients directing traffic at your application are directing it to the right node. But assuming we've striped our state out across multiple partitions, now we're finally in a position where we can start streaming, because now we've got these parallel processing swim lanes. We can stream requests in, and we can update state without undue blocking due to contention. It's still not the most optimal approach, because if we go back to my microsecond rule, if my application logic is residing here, and I need to update a piece of state there, and I need to do it in a consistent and reliable fashion, it still is a call out to an external data source, right? So how long does it take in your data center to replicate a piece of state to some sort of persistent storage? That's where this architecture gets a little bit more complicated to really push the amount of data you want in a cost-effective fashion. You can, of course, if you can stripe horizontally really wide, you can bring those processing lanes up and hit a larger amount of throughput, but you're going to be scaling wide, and it's not necessarily the most cost-effective approach. So, a little cognizant of time here, I'm going to sort of go through basically a summary of what we were just talking about quickly, but the biggest impediment here is having state outside of your application and any sort of call out you have to make, right? So that's going to be your fundamental gate on application throughput. And you as an application developer still need to manage the complexity of making sure your messaging stream and state streams stay in sync through some sort of distributed transaction technology. So what do we do in X? Our sort of architecture has always been one where we replicate state in a pipeline fashion, and more on that later. But we're beginning to see solutions like this hit the market in other places too. So Kafka's stream processing has a similar approach to doing this. So let me walk you through it, because I think it's useful to understand why these architectures really can stream a lot faster. So firstly, in X, what we do is we expose a model by which you can model state and messages as plain old Java objects. So you're going to model your messages and state in XML. We're going to generate just regular classes for you to use. And then we let you hold all of that state in memory, right? So we've instrumented that code so that while you're processing any sort of event, we're going to be able to keep track of what you're changing in your application. Now, bringing all of your state into memory, very simple, because now you're just working with collections and regular Java objects. But crucially, that 1 millisecond rule I had is no longer a factor, because now all of your state's just sitting there in local RAM, right? So, you're going to have a pretty big amount of, heap being used in your application, but it's all right there for you to use and update. Then the other sort of key simplification point that we do, and this one's sort of specific to X, is we make processing of any stream single-threaded. So your application code itself is in effect single-threaded. And what that allows us to do is have a guarantee that as we're processing a stream of inbound messages, there's going to be no contention even on the local host between any updates that you're going to do to any object that makes up your application state. So that really means that even down at a very low level, at the processor cache level, you don't have any contention to worry about, which again reduces the amount of time it takes us to process any particular event while you're doing your business logic. So combination of state in memory, single-threaded dispatch to application code allows you to process in the absolute fastest way possible, and you can start ingesting these streams really quickly. From a reliability standpoint, what's unique about what we do in X and somewhat similar in Kafka stream processing is once you single thread your business logic, you're now in a position to replicate any changes you make as a result of that processing, along with any sort of outbound events, to a backup instance to give you reliability. So any sort of processing I do, I'm going to change some state, generate some outbound messages. If you're single-threaded, you can replicate that state to a backup instance and begin processing the next request before getting any sort of stability acknowledgement from the backup. So that's really crucial in streaming, right? Because if I can start processing without having to wait for my data to be stabilized, I'm really in a position where I'm never blocking that stream from being processed, and I can use my hardware the most efficiently. So how would that be reliable? Well, as long as I don't send any outbound effects to the outside world, so I don't send any sort of outbound messages before the backup instance has remembered sort of my state changes, I'm totally fine with doing that, because if my primary instance fails, the backup instance can take over. It already has the state, and it knows what messages to send out. So the general flow in X for achieving reliability, an event comes in, you're going to update some state, you're going to send some outbound messages, we're going to replicate that to one or more backup instances asynchronously in the background. The backup will then have your state and sort of outbound messaging stream. If the primary fails, the backup can take over. If the primary doesn't fail, the backup would then acknowledge that, okay, good, I've got this data, I've got your messages, and it means that you can acknowledge the inbound request back to the messaging system. So the messaging system really only needs to be guaranteed in that if this application fails, it can replicate that event to a backup instance if it takes over to start the processing over. So in this fashion, we can do exactly once end-to-end processing of any sort of event that you're processing without blocking at all. This slide digs in a little bit more to that flow, and I'm going to come back to it if there are sort of questions on the reliability flow. So if we can use this pipeline replication approach, we can keep all state in memory, we can single thread your applications. What sort of performance can we now start expecting? All your states in memory, Once you're doing that, you've got data access that's, in nanoseconds rather than microseconds. So we're really gated in terms of how quickly you can process a stream of messages, more on how complex your business logic is. So if your business logic takes one or four microseconds to execute, now you can process events in a fully durable fashion at a rate of like 500,000 transactions per second, fully available. And this model makes your life easier because you as an application developer now are just working with regular Java objects in state. You don't worry about any sort of transaction management between making sure that events that you're processing are in sync with state changes you're making, because we're replicating both the outbound messages and the state changes transparently. And with a single threaded model of execution, you don't even have to worry about all that sort of concurrency nightmare of, what happens if I've got multiple threads updating the same piece of state at the same time. So all in all, an architecture like this, just by having state and memory, makes your life actually a lot simpler. So just to kind of summarize what we do in X, we allow you to treat your memory in your process as if it were durable. We expose semantics around messaging that are fire and forget, so any message you send, we're going to make sure that that will reach any particular participant, and that will be done in an exactly once fashion. So I want to quickly just sort of dive in, show you an example of how you might write an application like this. This is a quick app we built to write an event processor that can monitor a fleet of trucks, say like FedEx delivery trucks, and validate that their trucks are staying within sort of the expected bounds of the delivery route they're supposed to execute. So from an architectural point of view, it looks like just a bunch of processes. I've got some sort of gateway process that's sitting there listening to truck updates. And then I've got my vehicle event processor application where I want to look at location events and try to determine, is my truck following the route it's supposed to? If not, I want to send an alert because maybe that driver's stealing packages, or maybe a little bit less worse, just wasting gas. So this code is the entirety of what you'd write in sort of a memory-oriented approach to doing transaction processing. Just expose an event handler, accept a message type as a plain old Java object, some state. And if you look at this code carefully, you'll see there's no sort of infrastructural bleed related to transaction management, no synchronization. I'm just working with regular old Java objects, doing some processing, and sending some outbound messages. So from an application developer's point of view, this is really important in terms of remaining agile. We want you to be able to focus, only on the business problem at hand, and want you to be able to write pure domain logic that's related to your business without worrying about non-functional concerns. So you'd expose a handler like this to the platform, launch it up, and we're going to start delivering these location update events from that gateway straight into your application. So an application like that, this one performs at 130,000 transactions per second, fully durable, fully HA, fully persistent. So if the primary process crashes, we can take over from a backup instance and resume processing exactly where you left off. And at 130,000 transactions per second, our response time for any particular event averages out to a millisecond. So the usage of in-memory in this case has really allowed us to, at low latency, process kind of a huge stream of events. Oh, I didn't know that slide was still in there. So anyways, so why think about using an architecture like X or like Kafka? It really allows you to focus more on your business logic. You want infrastructure concerns out of your way. Focus on just your business problem at hand. And these systems, because they're using hardware more efficiently, it runs on stock hardware, it's got a lower total cost of ownership simply because you're not paying for as much hardware. You don't have to manage as much hardware. And of course, it's really, really fast. So very easy to get started with the X platform. I encourage you guys to check it out. We've got tutorials online. Plus today is the first day that we're launching our challenge app. Oh, you got it? Yeah. Take a look at Jan back there. We've got these cards. So this sweepstakes, chance to win $500. It'll take you, 30 minutes just to follow along our tutorial. We don't even really make you think. So I hope you think while you go through it, but it's just to sort of help you get a sense of how easy these sorts of architectures can be to maintain and use. So that's it. I wanted to kind of go through that quickly so we had a chance to take any questions. Do we have any questions out there? Hey, crickets. So up until recently, Kafka didn't support any sort of exactly once semantics, right? So it was, the onus was left on you as the developer to deal with redeliveries, any sort of duplication or sort of outbound transactional stuff. Another difference with Kafka is in their stream processing framework, they do replicated state to hot backup instances. The only difference is it's sort of the onus is on you to do the mapping from an actual business object into like a key value store. Other sort of differences is that when you're using their stream processing framework, they're going to use a more batched approach, so your latency is going to be a little bit higher, but effectively, you're still looking at like a ton of throughput. And so unless you're in like a really, really low latency system, it's sort of the same. It's just a little bit more difficult to use, I think. So with Kafka, you've got a few more moving parts, whereas the next application is just a self-contained process. Yeah, Java or Scala. So we've been looking at frameworks to put JavaScript on top. So as part of a cloud initiative that we're going for next year, we want to actually be able to run JavaScript that you'd sort of position online so you can just sort of very quickly tap into that JavaScript development pool. But for now, just Java and Scala.
You still have the duplicate issue with this, right? We have the same problem. So we get a lot of orders which is duplicate. So you have to go to the transaction to look up at least, and then throw out all the duplicate orders. And you said you're leaning towards a single threaded, and we have the same problem.
Yes, so let me sort of go back, and I want to talk about the duplication issue. So to do full exactly once delivery between applications, we can only do that within the set of applications that we manage, right? So we take care of duplicates in this case for an inbound messaging stream if it's coming from another X application. So you've written a multi-agent application that's got multiple components. As part of replicating your state changes and your outbound messages, we're also replicating the pointer to the inbound message stream that you're processing, right? So providing you're using an ordered messaging fabric, sort of say Kafka or Solace or something like that, the backup instance, if we have a failure, knows where it is in that stream and can filter out any duplicates transparently to you. So from an application developer point of view, you're only seeing an inbound event exactly once. Does that make sense?
See, if you are getting 10 messages and all of them are duplicate, it's going to process one after the other.
So if
and only one we needed.
So if you get 10 messages that are duplicates, you're saying a client application?
To go and look up again to the database to make sure that that has already gone in, or else how will you solve that?
So if I understand the question, you're saying I've got a message coming in and I'm not sure if I've already put it in the database?
Yep.
Okay. So in that case,
you're saying you have a duplicate message
That copy, 10,
from a client.
problem. Client doesn't take care. We'd have to take care of that.
Okay, so yeah, so an application's got some sort of bug where it's going to send, the user clicks a button twice, for example, in that case.
Something like that, or their batch process doesn't run properly, and they just, if the acknowledgement doesn't come within so much millisecond, they send it back again.
So yes, if they're in your application logic, there is the chance that due to bugs upstream or you know, user error upstream, you still need to handle any sort of user error in that case. So when we say exactly once processing, we mean of any actual message that you produce. Now, if your sender happens to be X, that sort of duplicate that you're talking about only happens if your business logic sends the same message twice, you know, or same logical message twice. It's just not going to happen with the you know, execution framework that we have here in terms of like a physical message on the network. So does that make sense? Yes, if there are sort of application errors or sort of application error conditions, you do need to handle that. We don't get into you know, handling your business logic. I think you had one more question too, right? Was there, oh, there was a follow-up? Okay, cool. Yes. Oh, 1 second, she's going to give you the mic.
So the stream can hear. Thank you.
So this is like a serverless sort of architecture, like AWS Lambda. Like I would write up a handler, and I would just I would somehow register it as a handler, and I would update it through some build tool that you have.
Yes, so not quite serverless. When you write these applications, what you're going to give us is a collection of event handlers, you know, sort of sitting in classes somewhere. You can deploy that to AWS, but we're still sort of running the container in which that logic runs. So sort of underneath it, yes, it looks like just a collection of event handlers that you write, but it's not quite serverless in that we don't yet have a cloud offering that takes care of that piece for you. We do have tools that make it extremely easy to deploy that to a variety of different clouds. So it's a little bit like serverless, but we're not at the point where we would call ourselves like a platform as a service just yet, or infrastructure as a service. But the programming model's the same.
So if I wanted to like install some third-party library, either at the like the language level or at the OS level, that would be like
totally cool. Yep.
Okay.
So any sort of Java you can do. The only sort of caution is that you don't want that library doing anything that's kind of blocking in nature if you're really trying to stream. And the platform's not, you know, we don't only do streaming. We're sort of a general purpose application platform. But yeah, anything you can do in Java, anything you can do in Scala, knock yourself out.
Cool, thanks.
Thank you. Any other questions out there? Yes, one more in the back.
Let's see if this is too loud. Okay, so it made me a little scared when I saw, you know, a little bit of this action. So, sorry. I noticed you had an app demo in GitHub. Is any part of the X platform? Sorry, I was trying to manage that. Any part of the X platform open source?
Yes, so the core transaction machinery is closed source, but we offer a free license, and the only limit on that is on the maximum amount of heap size. So we limit you to 8 gig of heap with a free license for the platform, and that one is closed source. There are various frameworks built on top of the platform outside of that core transaction machinery for doing request reply. So we have a framework called Eagle that is really geared towards talking to HTTP front ends. And we have another framework called Hornet that's geared towards doing sort of very topic-rich applications in sort of a streaming case. So there's a lot of that that's open source that's you'll find in our GitHub account. And yeah, of course, check out sort of sample applications and demo applications there too. It gives you a good sense of what it takes to build one of these things. Thanks for the question. Anything else? More challenging questions on how we do X once? Okay.
All right. You
Cool.
guys give it up for Colin. Thanks, Colin.
Thanks, everyone.
That was great. You'll be around after for questions, further discussion.
Oh, yes, absolutely. I'm here for a while and want to eat some pizza. So.
Yeah, there you go. Hit Colin up. So tomorrow, first annual Startup Week Parade is going to be right out front, right, Alex? You're partaking. You built a robot for this. There's going to be robots. At least 3 robots. Maybe. Definitely 3, but maybe more. They may not all work, Alex says. So come and find out whether the robots will work. 5:30 tomorrow. There's going to be a lot of people partaking, and we'd love to have you. See you guys then. Have a good one.